Hi, welcome to Unit 2.2a. This is part 3. You've previously watched part 1 and part 2, and that was about a week ago. And now we're moving on to part 3, so it's the same packet. Just so you know that there are some supplemental videos embedded in this video as well as linked in the activity. All right, in this video we're going to learn about net ionic equations. And they're useful because they simply simplify double replacement reactions like neutralization and precipitation reactions. And they simplify it to the most essential information. So the process is the same no matter what. For the other key thing to know is for Brown's lauric acid and base neutralization reactions, all net ionic equations look like this: H plus, OH minus, and H goes to form H2O, liquid. Precipitates look similar. You'll have an anion, a cation, and a solid. So these are typically what they look like. Let's look at some examples. So for the first example, we're going to go through the process. This first example is a precipitate reaction. And remember, with a precipitate reaction, you take two aqueous solutions of salts or ionic compounds, and when you mix them together, you should get two new salts. At least one of the salts must be insoluble in water, so its phase is going to be written as a solid, not aqueous. So let's take a look. Let's say, for example, you had a potassium chloride solution and you mixed it with silver nitrate. All right, so according to our double exchange, the potassium will go with the nitrate and the silver will go with the chloride. And the products are going to be potassium nitrate and silver chloride. In order for you to know which one of these is the precipitate, you have to rely on your solubility rules. So the reactants are going to be aqueous because these are two solutions that we're mixing together. But for the products, you need to figure out which one is going to be a solid. So let's talk about the first product, potassium nitrate. According to our solubility rules, all group 1 compounds are soluble, and also all nitrate compounds are soluble. So we know that from either one or the other, or both in this case, that this is going to be soluble, so we write its phase symbol as aqueous. So when something is soluble, it will be aqueous. The other product, silver chloride, on the other hand, is insoluble. And how do we know that? According to the solubility rule, all chlorides are soluble with the exception of lead 2, dimercury, and silver. So as a result, this one is going to be insoluble because it's one of the exceptions to the chloride solubility. And so since it's insoluble, its phase is going to be solid. So the molecular equation, as you can see, is the typical way that we write the equation in their molecular forms. And that's our first step. The next step is to write what's called a complete ionic equation. And for this, what you're going to do is you're going to break everything that's aqueous down into its ions. So for example, potassium chloride, it's in an aqueous phase, so we're going to break it into ions. Silver nitrate, it's in an aqueous phase, so we're going to break it into ions. Potassium nitrate, it's in an aqueous phase, so we're going to break it into ions. But silver chloride is solid, so we're going to keep it in its molecular form. And essentially what that means is we're going to keep it as is. So what's it look like when we break everything else down into ions? It's sort of like what you did when you were doing the dissolution or the reactions where you're dissolving salts. Potassium chloride breaks down to K plus and Cl minus. The charges, we can get that from the groups that they're in. So group 1 metals have a +1 charge, and group 17s have a -1. Silver nitrate breaks down into Ag plus and NO3 minus. So NO3 minus is a polyatomic ion. You have to remember the charges of the polyatomic ion. And silver is, unlike most transition metals where they have varied charges, silver is typically +1. You can also just determine that based on the fact that the polyatomic ion has a -1 charge, and so this one must have a +1 charge in order for the charges to balance. Now let's go into potassium nitrate. That breaks into K plus and NO3 minus, and it's for the same reasons we mentioned before. And remember, silver chloride is a solid, so we're not going to break it apart. We just rewrite it as is. All right, so this is called a complete ionic equation because everything that you can write into ions is written into ions. The next thing we're going to do is we're going to do what is actually the fun part, and that is crossing out species that are ions on both sides. So if you had me as an Algebra 2 teacher, you know I'm really big into crossing things out. I like to think of it as me like whipping out a samurai sword and just taking them out. So we're going to cross things out that are ions on both sides. I'll show you an example of that. And what's left is the net ionic equation. So let's take a look. Let's start with potassium. That's the first species I see. It's an ion on the reactant side. So now I need to find it on the product side. Here it is on the product. So potassium's here. It has a +1 charge as well as an ion as well. So since it's an ion on both sides, reactant and product, I can take them out. Let's do the same thing for the next one. Chloride. It's an ion on the reactant side, but on the product side, it's a part of this molecule. And so it's not an ion on both sides. So we cannot cross it out. Silver is an ion on the reactant side, but again, on the product side, it's the molecule, so we can't cross it out. And then finally, nitrate is an ion on the reactant side and also on the product side, so luckily we can take it out. Okay, so now, once we've done that, what's left is what's called a net ionic equation, and what we have left is chloride ion, silver ion, and then silver chloride solid on the product side. And so this is our net ionic equation, whatever we did not cancel out. You probably can see the pattern that when you do a net ionic equation, essentially what's ever written as a solid on the product side, or is something that's not aqueous on the product side, you're going to write as ions on the reactant side. So I'll say that again. Since silver chloride is not in an aqueous form, so our product silver chloride is not in an aqueous form, then you, on the reactant side, is going to be the ions of silver chloride. That's a shortcut, but it usually works for these problems, but it may not work for all problems. All right, so before I move on and look at another example, I just want to speak about what we call the things that we cancel out. They actually have a special term. They're called spectator ions. So potassium and nitrate are spectator ions. And the reason why they're spectator ions is because just like in a sports game, spectators, they're there, but they're not really doing anything. They're not playing the game, right? So the same thing's happening here. Potassium and nitrate, they're there, but they're not really doing anything. What do I mean by that? Potassium ions you see potassium is an ion on the reactant side and also on the product side. So that means it didn't really change. It didn't really undergo a chemical reaction in this aqueous solution. Same thing with nitrate. It's an ion on the reactant and on the product side. So it also didn't change. So it really didn't do anything. The only things that really did anything were the chloride ions and the silver ions because they form the product silver chloride. And so they form something new. They did change. And so that's why they are like the main players. All right, we're going to look at one more example where we follow these steps to do the net ionic equation, molecular equation, then complete an ionic equation, and then cross out species on both sides. Okay, so here's our second example. We're looking at an acid-base neutralization. So let's start off with the molecular equation. In this acid-base neutralization, we are reacting hydrochloric acid, or HCl, and sodium hydroxide, NaOH. And remember, an acid and a base yields a salt, which is NaCl, plus a water. So you really ought to memorize that. Acid and a base yields a salt plus a water. An acid and a base yields a salt plus a water. An acid and a base yields a salt plus a water. That's one of those things that you really need to memorize because that's going to be super helpful whenever predicting products of an acid-base reaction. Okay, now let's get into going back to net ionic equations. Our next step after writing the molecular equation is to write the complete ionic equation. And remember, there's only certain things we can break apart into ions. So take a look at this molecular equation. Which species can we break apart into ions? That's right, we can break apart HCl, NaOH, and NaCl because they are all in aqueous form. Water, which I've written here as HOH, but I can also write it as H2O, is in liquid form, so we cannot, a liquid phase, so we cannot break it apart. All right, so this is what it looks like when I break it apart into their ions, H+, Cl-, Na+, OH-. On the product side, we have HOH, which is again just water, Na+, and Cl-. Okay, the next step is to cross out any species that are ions on both sides, and what's left will be our net ionic equation. So we're starting off with H+. It's aqueous ion on the H+ on the reactant side. But on the product side, the H is in the water, which is liquid, so we do not break that apart. So that means we can't cross out H+. Cl- is an aqueous phase on both sides, so we can definitely cross those out. Na+ is an aqueous phase on both sides, so we can cross those out. And then OH- is aqueous phase on the reactant side, but on the product side is a part of this molecule here, water. So we cannot cross it out. Okay, so what we have left is our of course, our net ionic equation. And remember, I wrote the HOH instead of H2O just so that we can see that this is a double exchange reaction, meaning that the proton in, or the hydrogen in the acid will react with the OH in the base, and to show that those two exchange. But when you're really writing this, you would write this as H2O. So I'm just going to rewrite it as H2O here. Okay, now let's take a look. Which one of these would be our spectator ion? So go back to the complete ionic equation, find your spectator ion. That's right, Na plus and Cl minus are our spectator ions because they cancel out. Those are the things that they're not really doing anything for this reaction. All right, if you are looking at this stuff and you're like, I would like to see some more examples, I have linked 2 supplemental videos on ionic equations. You can watch those videos if you need additional help. Those videos are super helpful, especially because they give you more examples, particularly examples where you have something like PbNO3 where you have 2 anions. How do you break something like that apart? If you want to see what you would do in that case, these videos may be helpful. Okay, so after watching those videos, if you chose to watch them or not, these are some net ionic equations that you're going to practice. This actually comes from CFU 1. You're going to write the net ionic equations, and I gave you the molecular equation. The third one here says no reaction, and you may need to go back and see your notes for that, why this would be considered no reaction. But at any rate, for this problem where there's no reaction, you will not be able to, I'm just going to tell you now, you're not going to be able to write a net ionic equation. However, I want you to write a complete ionic equation and cross out everything you can cross out, and that will show you why there's no reaction. All right, pause this video now and try writing the net ionic equations for these 4 reactions, and when you press play again, the answer will be revealed. All right, so here are your answers. For the third one here where it says no reaction, the reason why it should be no reaction is because all of the ions are spectator ions, meaning you cross out everything. And so as a result, there's nothing left. And so that's why there will be no net ionic equation. You cannot do it for here. But for the rest of them, you should be able to write net ionic equations, and this is what they look like. Remember, acid and base reactions all pretty much look the same. Okay. We are now going to move on to part 4. So this is the end of this video, and I'll see you at part 4. Have a quality day.